I am pleased to present to you Matthius Bicknell on the topic of the energy of our future.
You may have heard of fission, a process of splitting atoms to create large amounts of energy. Fission, although a fairly clean energy source in terms of greenhouse gas emissions, produces radioactive waste that is very damaging to the environment if treated improperly. Fission reactors, you might know them as nuclear reactors, are susceptible to nuclear meltdown. A nuclear meltdown occurs when the fuel overheats and begins to melt the container that's held in. This releases radiation into the surrounding environment and creates lasting effects. Some of the most infamous nuclear meltdowns that have occurred are the Russian Chernobyl explosion and the more recently Fukushima nuclear meltdown. But what if there's a different energy source that's way cleaner and way less dangerous? Well, there is. Nuclear fusion. Hello, my name's Matthius Bicknell and welcome to my Masterworks. So, what is fusion? Fusion is the extraordinary process of taking two light atoms, something like helium or hydrogen, and combining them into something heavier, like iron. This process has been happening in the stars for billions and billions of years, and is the main reason for all of our modern day elements. The process of fusion begins when two atoms, here, deuterium and tritium, are collided together at ridiculously high temperatures of 100 million degrees Celsius. When these collisions take place, massive energy is released. But this is definitely not as easy as it sounds, as you're literally creating a mini sun inside your reactor. First and foremost is a problem that you have to heat a gas to an incredibly high temperature just to create the environment for fusion to occur. To create this heat, scientists basically throw all forms and all types of heating techniques at the gas, which will turn into a plasma, and then heat that gas up to the temperature for fusion. However, once you have created the plasma, the second obstacle that scientists have to tackle is actually containing it. The most common way to hold plasma is to hold it in a large tritial or donut shape, surrounded with supermagnets and held in a vacuum. But even though there's struggle, scientists have been able to produce fusion. The ways that I'll be teaching you about today are tokamak fusion, inertial confinement fusion, which is just a sciencey term for laser fusion, and magnetized target fusion. Now, all these reactors are different, using a multitude of strategies to produce and to create fusion. The first and most researched method is the tokamak reactor. This machine works by heating gas into a plasma, and then heating that plasma up to that 100 million degrees, which is also 6 times the temperature of the sun. Then they circulate this through the machine and confining it with magnetic fields. It has some key features that make it work. A vacuum in which the plasma is held in, the plasma which is the fuel for the actual reaction, and a magnetic field that and a phenomenal amount of energy to actually create fusion. The most difficult part of this process is, of course, cooking the plasma up to fusion temperature. The way that tokamak reactors and the scientists do this is by using plasma current, which is running electric current through the plasma, radio frequency heating, which is a huge microwave, and neutral beam injection. When the reactor reaches the right amount of heat, fusion begins to occur in the plasma. The atoms in the plasma begin to hit each other and fuse together creating helium and also a large amount of energy. The reason that plasma needs to be so hot is because fusing atoms is kind of like trying to stick two magnets with the same charge together. If you do it slowly and without a lot of force, they don't want to touch, and the closer they get, the more that they don't want to touch. However, if you use enough speed and enough force, the magnets will touch, and in fusion's case, they'll create a lot of energy and create a new element on the periodic table. So the relationship between these two, this analogy and fusion, is that if you replace those magnets as atoms and the force at which you're throwing the magnets at each other with millions of degrees of temperature, the atoms will touch. Laser fusion is the next type of fusion reactor. It creates fusion by compressing a fuel target the size of a pinhead, which only holds about 10 milligrams of fuel. The system uses an array of lasers to heat the outer layer of the pellet so much that it combusts. This is shown by the arrows flying off of the surface of the pellet. This combustion, it kind of acts like a rocket booster. While there's some energy propelled outwards, there's also energy propelled inwards, compressing the center of the pellet. If this compression made by this combustion is powerful enough, it will create fusion at the center of the pellet. All the criteria for fusion are met in this pellet, as during this reaction, the pellet is at 100 million degrees Celsius. So far, scientists have been able to produce this reaction. However, they're pursuing a process called ignition. This is, if the first fusion reaction that happens within the pellet is hot enough and produces enough energy, it'll make a chain of fusion reactions within the pellet that uses up all of the fuel. More energy is produced overall, and laser fusion becomes a very, very powerful source of energy. However, they haven't succeeded, as they only have 1/3 of the energy required for the ignition technique to actually occur. The next reactor is something called magnetized target fusion. This was developed by a company called General Fusion. It was actually started on Bowen by a man called Michel Laberge. He actually created fusion in a garage on Bowen, and from this fusion reaction, he got a loan, and he built a company called General Fusion. Now, this is important to me, as one of my external advisors, Michael Delage, is one of the employees and scientists that's working on this kind of fusion. I visited this company's base of operations in Burnaby to learn directly from the best. Because after all, like I said before, Mike Delage works there. This was definitely the highlight of my Masterworks journey, as I learned so much and had fun while doing it. In this excursion, I learned just how their fusion reactor works. MTF, this is a picture of me in front of their prototype. Their fusion reactor works using a technique called the hammer and anvil. This utilizes a plasma injector, which is these things, a vat of molten lead lithium, which is this in the center, and compressed gas-powered pistons, which are these things that are surrounding the vat. To start the reaction, MTF uses the plasma injector. The plasma injector is comprised of a cone within a cone. Sorry if the people in the back can't see it, but it's kind of like this, and there's a space between the two cones where gas is injected. The gas is then blasted with 20,000 volts of electricity, and just to put that in perspective, that's briefly equivalent to all the power used in BC at any moment. So it's a lot of energy getting blasted into the gas. This turns it directly into a plasma, and this plasma will again be used as a fuel for the fusion reaction. This newly created plasma then travels down the channel between these two cones, compressing as it does so and heating up more. And then flying down into the center of a vortex created in a swirling vat of molten lead lithium. When I say vortex, I mean that the vat of molten lead lithium is being spun around fast and creating kind of like a hole in the middle, kind of like what happens when you drain the water from a sink and you get that vortex, as you call it, in the center. This tiny ring of plasma is shot in the center of this vortex. This is when the monstrous gas-powered pistons come into play. The pistons are propelled with compressed gas, as the name implies, down a sealed chamber and slamming down on another circular steel cylinder, or anvil, called the anvil, and the piston is called the hammer. This creates a shock wave through the vat of molten lead lithium, and compressing the vortex at the center of it, and then after that, compressing the plasma. This crushes it so ridiculously fast that it creates all the heat needed for fusion to occur. Originally, general fusion decided on having lots of big hammers, as you can see here, but got rid of that idea for kind of the same reason that if you're trying to squish a water balloon, or regular balloon, if you're trying to squeeze it with only your two hands, it likes to go the different directions and doesn't actually go where you want it to go. Plasma acts in sort of the same way and doesn't want to be compressed. So they changed to having a lot of different, here I can use the laser pointer, a lot of different, or a bunch of hammers so that they get a more uniform shockwave throughout the molten vat of lead lithium. They decided, conversely, therefore, with more pistons, general fusion would have more control over the reaction, creating a more uniform shockwave, and then having more energy, and more energy is produced from this compression. After all, the pistons do 98% of the work used for plasma and fusion to occur. Or not plasma, for fusion to occur. These parts, or the compressed gas powered pistons, are fairly cost efficient. Cost efficient in fusion land is like 200 million, so pretty expensive still. But this is still less expensive than the billions of dollars that are the cost for the lasers used in the laser fusion that I showed before. This is like what the reaction for general fusion kind of looks like. All of these surrounding are the pistons, which slam down on this vat of molten lead lithium, which is being swirled around to create this vortex that you see in the middle. Plasma is injected from the top in that tiny ring that you see flying down, and it's met just when the shockwave created by the pistons hit it, and everything's compressed. Fusion reactors are very clean and efficient. They produce no emissions, well, almost no emissions. The emissions that they do release are very small, although some of the construction emissions that are produced along the way can be large, as a lot of heavy machinery is required to build these fusion reactors, as some of them can be 10 stories tall. But in the long run, fusion creates a lot of energy, and it runs so clean that it'll be made up for by a lot in the end. So where's fusion today? There are the three largest reactors for each of these techniques that I described. There's first ITER, which is being built in France, and it's a worldwide collaboration to create probably and hopefully the first fusion reactor that'll be used commonplace. The next reactor that uses laser fusion is called NIF, the National Ignition Facility. And of course, I've already talked about general fusion. All of these reactors have potential to be the most powerful, or probably the first reactor to be used by normal people like us and used to power cities. But so far, no matter how large or how smart and how much research that we've done, we haven't been able to produce net energy, or the same amount of energy that we put in, we get out of the reactor. This also means that 20,000 volts that we use to ionize the general fusion's plasma is not equivalent to the energy that we're getting out of the fusion reaction that they've produced. So then, why fusion if we haven't been even able to produce a fusion reaction? Well, it's because in my belief that it's our best bet for the future. If you ask any fusion scientist, like, when will we be running on fusion? If you ask 500 years, they'll say we'll definitely be running on fusion. If you ask 100 years, most likely we'll be running completely on fusion. 50 years, probably. 10 years, maybe. But this is actually a really good sign, because 10 years, while it might seem far off now, isn't very long compared to the scope of how long that we've been creating power. So if we could actually have fusion in the next 10 to 50 years, that would be incredible, and most of our environmental problems would be solved. We all know that it's struggling and that fossil fuels aren't the answer for our energy problems. So for these reasons, I believe that fusion is the energy of the future. I want to thank all of my advisors who helped me like hugely through the process. I started off thinking that I had like a general grasp of this topic, and I found out about a month in that I didn't know anything at all. Michael Delage, the guy who works at General Fusion, he's incredibly smart. He taught me so much. I could only learn so much reading from websites, books about General Fusion. Just having someone telling me and explaining to me the process of fusion and how it's created helped my understanding go so much farther than it would have gone. Reed Vimet, my other external advisor, he helped me so much with the editing and just general knowledge on science. I could just ask him any question that I wanted, and I would get some form of answer that would help me on my way. My paper is pretty rough in the first draft. He did so much editing and so much work throughout it, asking me thought-provoking questions that improved my learning throughout. And lastly, Pam Matthews for being my internal advisor, keeping me on track and helping me keep with all the deadlines. And also for my mom and dad, because my mom stayed up really late one night, probably helping me edit my paper for 5 hours, staying up to almost 1. It's pretty ridiculous and pretty heartwarming actually for me. And my dad just for giving me all the ideas for actually starting this project.
I am very pleased to announce that Mr. Mattheus Bicknell has met all the requirements of the Masterworks program at Island Pacific School.